Yeah. So the topic that I'm going to talk about today is actually a very important one, at least for applications, and this is called projection operators. And the basic idea really is very simple. We have been saying over and over again that in most physical applications, or in fact in most applications, when you get a natural representation of a group from by some method, that representation would usually be reducible. It's not going to be irreducible in general. And so what that means is if you were to choose your basis correctly, or if you were to choose your basis carefully, what you will be able to do is reduce all the matrices for the representation into a block diagonal form. And we have been saying that once you get it into the block diagonal form, you can derive many useful results out of that. If I get enough time today, I'm going to at least indicate one of those very important useful results. But I'm not sure whether I will get time after completing this part, but let's see. But the basic point is, if a representation is reducible, then what we do know is that the representation is going to be, then you should be able to break up the representation into small chunks. The basic idea is every representation is on some vector space, and if the representation is reducible, then there are non-trivial subspaces of this vector space which are invariant under the action of all the group elements. And that means that if you were to just focus on the vectors which are in those subspaces, they themselves will alone furnish a representation. And when you apply all these operators corresponding to the group elements on these vectors, you're only going to get vectors in that subspace, and which is the reason why you get this block diagonal structure. Now, all that is fine, and for many applications, you don't even need to know what these representations are. For many applications, all you really need to know is how many such irreps going to make a reducible representation, and you can find that out simply by looking at the character table and using the character orthogonality theorem. Right? So, just so that we are on the same page here, let me remind you of a calculation we have done several times before. In fact, at least in the lecture videos, also in this particular in these discussion classes, we have done this before. This is S3, the symmetry group of a equilateral triangle, and as we had figured out earlier, it has three classes, so three irreps. And if you look at the character table, corresponding to these three irreps, A1, A2, and the third one is usually called E, although some people, and in fact I have also done it in this video that I'm preparing, some people do call it B, but the standard notation is usually A1, E2, and the second two-dimensional one is called E. The reason behind that is somewhere in the German terms which were originally used. So these are the characters corresponding to the group elements. And of course, as you know, A, B, C, the three reflections are in the same class, so they all will definitely have the same character. DF will also have the same character. E always has a character, is in a class by its own, and these are the characters that you get. Okay. Now, the particular reducible, these are for the irreps. The particular reducible representation I'm talking about, whose characters are given here, is also something that you are familiar with. We have seen this before, although we have been promising that this will be a center stage of a very important set of applications, but we have not really got to the physical application yet. Hopefully soon. But let me just remind you, we were talking about molecular vibrations of a triangular equilateral triangle shaped molecule, and in 2 dimensions at least, we could actually write down any displacement of the atoms in terms of these 6 basis vectors, which we have called E1, E2, E3, E4, E5, and E6. So a general displacement configuration would be this atom would be somewhere, this atom would be somewhere, and this atom would be somewhere else. And I would be able to write down new configuration of the molecule in terms of these basis vectors E1 through E6. And then we figured out what happens when we apply any one of these symmetry operations, E, A, B, C, D, F, on these basis vectors, and that helped us to produce a 6-dimensional representation of this group. Now, as you of course all know, the irreps of this group, there are 3 of them, 2 one-dimensional, 1 2-dimensional. We have just seen the character table a while ago. And that means obviously that the 6-dimensional representation has to be reducible, cannot be irreducible. And in order to find out the reduction, what we needed to do was simply look at the character table. That was enough. Of course, what we needed to do is first figure out what the characters for each of the group elements would be for the representation furnished on this 6-dimensional vector space. For the identity, of course, the character is trivial. The identity operator in any vector space is always represented by the identity matrix. So this character is always 6, always the dimension of the representation. In this case, 6. For the other characters, we have done this before, but let me just quickly remind you. Let me just show you one example. If you did A, for example, what will happen is that this atom here would flip to this atom here, this atom would flip to this atom here, right? So, for example, this basis vector E3 will be a displacement now, but not of this atom at this corner, but of this atom, and it will be pointing this way. So E3 will change it over to E3 prime, this blue vector here, and E3 prime is of course minus E5. Similarly, E4 becomes E6. E5, this vector under reflection along this vertical line becomes this one, which is minus E3, and so on. Using this, of course, you can figure out the full 6x6 matrix. In this case, the 6x6 matrix is a rather trivial, simple one. However, all we are really interested in, or at least all we were really interested in prior to this class, was in the character for this particular element. And for the character, you just have to add up the diagonal elements, which means that among E3, E4, E5, E6, these are displacements corresponding to 2 atoms which have switched under this particular reflection. So obviously E3 after reflection will have no E3 component, right? E3 after all is a displacement of this atom. After you reflect, whatever displacement you have is of this atom here. So E3 of course will not have any E3 piece. As a result, E3, E4, E5, E6, the displacements corresponding to these 2 molecules which have moved under the reflection will definitely not contribute to the trace. Okay? Is that clear to everybody? Yes, if there's any confusion, let me know. I've already done this several times before, so I hope it should be okay. The only thing which can possibly contribute to the trace is the atom here, which has not budged under the reflection. But under this reflection, E1 obviously becomes minus E1 and E2 becomes plus E2. So these 2 quantities contribute to the diagonal, non-zero amounts to the diagonal, but they contribute minus 1 and plus 1 respectively, which means when you add up the diagonal elements, you are going to get 0. So this one has this LA has a corresponding matrix representation of trace is 0. Very, very similarly, you can show that for all the others, for example, for B, which is a reflection along this line, let's say, this particular atom, the atom whose displacements are characterized by E3 and E4 components, this one will not budge. The other 2 will switch places. So for the other 2, I don't care when we are considering the trace. The other 2 will not contribute to the trace at all. The only possible contribution to the trace will come from E3 and E4. But if you figure it out, what happens is E3 on this reflection becomes a vector which is rotated through 60 degrees, right? Because this angle is 30 degrees. So this angle becomes 60. So you can easily figure out that E3 becomes half E3 plus root 3 by 2 E4. And similarly, E4, under a reflection in this line, it was making 60 degree on this side, so it will now make 60 degree on the other side. So it will actually make 30 degree to the horizontal axis on the other side. And you can easily figure out what E4 is. And you can easily see that E3 and E4 both contribute half and minus half to the diagonal, and hence the trace again is 0. Things are even simpler for the rotations. For D and F, the situation is very trivial. For D and for F, all the atoms move. So E1, after you rotate it, will definitely not have any E1, E2, any E1 component or any E2 component. I'm really interested in whether E1 has any E1 component after rotating, because that's what's going to contribute to the trace. And I found out that no such contribution can occur for any one of these. So for both rotations, you're going to get trace of 0. So that actually gives us this particular entry in the character table. Usually when we write down the character table, we only write down the character table for the irreps, but we have added one more row simply for the representation that I'm dealing with right now. And decomposition of this can be figured out using our character orthogonality theorem and all these calculations that we had shown how to do. But you don't even need to do this, because you already know a representation which is going to have exactly this character. A representation in which the identity has a character which is equal to the number of elements of the group, and every other element has 0 as character. What that means is that this representation has to be equivalent. This is not the regular representation. The matrices are of course not the same. The matrices are quite non-trivial if you write down the 6 by 6 matrices. Apart from that, for E and A, the other matrices would have non-trivial elements in them. The regular representation only has matrices in which every column and every row has a single 1, all the rest are 0. This particular representation is not the regular representation, but the character actually tells you that this has to be equivalent to the regular representation. Anyways, only the character which decides on what kind of irreps this particular representation contains. So because the characters here match with that of the regular representation, you know that this particular representation has to be a direct sum of each and every one of the irreps which the group has, taken as many times as a dimensionality of that irrep. So it has to be A1 plus A2 plus twice, right? So up to this is old stuff. We have done this before, but are there any questions about this? None.
Sir,
yeah.
Could you move to the diagram, triangle?
Okay. Which one?
Yes, sir, anyone will do. I mean, okay, the first one is okay. The first one.
The very first one, yeah.
Okay. So we are using the formula chi-g is trace of dg, right? So we're picking a group element, and then we're trying to find its character using this formula trace of dg.
Yeah.
Okay.
But when you calculate the character, let me just say one thing. When you're calculating the character, what you're really doing is that for each basis vector, you're asking, after I do the operation, how much of that particular basis vector, the original one on which I applied the operation, how much of that is still in there. Okay, and then you have to add up that. So that is going to be your diagonal element. And then you add them all together. Okay?
Yes, sir. Got it.
So if you, for example, if you do the rotations, apart from the identity, which is also a rotation, but identity, of course, nothing moves. Everything contributes exactly 1 to the character, and 1 to the diagonal, and hence to the character. So the identity will have 6. For the other operations, all you have to worry about is just focus on the atom which does not move under that operation. For the two non-trivial rotations, every atom moves, so they trivially have a character of 0. Anyway, character being a class function, remember you have to calculate it only for one of the class elements. You don't really have to calculate it for both D and F, or for A, B, and C. If you have calculated it for A, that's enough to figure out that it's going to be what it is going to be for B and C. But you could of course try to do that explicit calculation, and if you did that, of course you are going to get the same result. That is, you are going to get these characters. Okay, and using these characters, you can figure out this decomposition. Yeah.
So,
Yes?
so you're saying when we rotate, So we are actually like changing the vertices. So no basis vector goes to itself. That is what you're trying to say.
Yeah,
And
no
hence its
basis vector
contribution
has
in
a
the trace is zero.
component. No basis vector
Okay,
has a
okay,
component which in terms of itself,
okay. Yeah.
right? Because, for example, even for say LF or not LF, let's say LB, the one which you have seen. Even there, this particular E3, E4, they don't go into themselves, but E3, E4 can now be still expressed in terms of E3, E4. So E3 at least has an E3 component. E3 becomes E3 prime, but that has an E3 component. So this could have contributed to the trace. It doesn't. That's a different story. If you add up the two contributions from, okay, they do contribute to the trace, but when you add up the total contribution, you still get zero. Okay. But in fact, this complicated calculation involving E3 I did not really have to do, because all I needed to do was calculate it for LA. That is simpler, right? And A, B, C being in the same class would have told you that the character has to be the same, right? So since for A, all you have to see is take a look at E1, it becomes minus E1, E2 stays E2. The two contributions are minus 1 and 1 respectively, and they add up to 0. That's it. Okay. Right?
Okay, so we have to add all of them. As in E2 has a component along E2, obviously, but you
Yeah.
have to add all of them. Okay.
Of course,
Yeah.
that's a trace, right? You have to add up all these
Yes,
contributions.
yes, yes.
If
Yes.
something doesn't have a contribution, you can simply forget about it. That's why here, for example, for LA, I did not worry about these pieces at all. I just focused on this particular atom because this is the only one which can contribute anything. Both E1 and E2 do contribute. They contribute opposite amounts, so the overall thing cancels.
Yep.
Is that
Yes.
okay? But the overall thing is the trace. And that's why you end up with 0 there. And I said it will be slightly more complicated to calculate the trace for B, for character for B, but you don't even have to do that. You know that B is in the same class as A, so you know it has the same trace. Okay, so this particular lengthy calculation that I've written down here, you don't really need it, at least not for character calculation. Okay.
Yes, sir.
Now the question is, this is the old stuff, so not something we are going to be. It's just background for what I'm going to talk about today. Really, we know that this particular representation, which has nice physical meaning about molecular corresponding to molecular vibrations, is a direct sum of three irreducible representations. Not really three, four actually: A1, A2, and two copies of E. Okay, right? So the question that we are going to ask is, it's fine to know that this is what is inside the representation, but it will be even more important for us, especially when we want to look at what kind of vibrations this molecule can have. It would be very, very nice to know exactly which basis vectors actually correspond to which particular representation that we have. That is, these irreps that you see, what kind of basis vectors would you start with? Not your original basis vectors. For example, you can easily see that A1 essentially has a character of 1 for each and every one of the group elements. Not only does it have a character of 1, it's a one-dimensional representation, so it's really a representation where each and every one of the matrices involved is just the number 1. What that means is that it is talking about a particular kind of displacement which the atom molecule can have, which will stay the same under each and every one of the group operations. It's not very difficult to figure that out. We did figure that out in an earlier class. We just sort of argued what kind of displacement can it be which stays the same under all of these. Just hold on. Let me take this call. Yes. Okay. So, but here, at least for A1, the basis vector which actually corresponds to A1 is sort of easy to figure out. A2 not so much. And the two E's, again, if you did not know the answer, it would not really be very easy to figure that out. Okay. So the point is, we will often need to know not just which irreducible representations actually build up your reducible representation, you would also need to know which vectors really carry those irreducible representations, or which particular vectors transform under those irreducible representations. And for that, we need to figure out a change of basis. That is, just saying that, okay, because this is reducible, you should be able to find a new basis in which all of these matrices become block diagonal. That's fine, but just saying that is not enough. You would have to actually find that basis. And that is where these projection operators come in. Okay. So I hope the motivation is clear to everybody. That is why we are going to study projection operators at all. So let us just start with the projection operator business now. So first of all, you have to remember that if you have a reducible representation, then it's really, then the underlying vector space on which this representation acts, the stage on which the representation is playing itself out, is a direct sum of invariant, non-trivial, of course, that goes without saying, non-trivial invariant subspaces. I hope everybody remembers what this means. And a consequence of this is any vector small v belonging to our vector space can be written down as, say, v1 plus v2 plus and so on. Many vectors where v1 is in one of the invariant subspaces, v2 is in another invariant subspace, v3 is in another invariant subspace, and so on. That's what a direct sum is, right? You can write down the actual vector as a sum of pieces, each one of which belongs to these subspaces. And because the subspaces are invariant, when you apply any of the group elements, they will transform only to a member of that subspace, not outside that. So what makes this very useful for us is that we can actually find out a basis set for the entire original vector space, capital V, which goes like this. What you could say is, let's take a particular representation. Let's take the representation, irreducible representation. I'm going to talk of an irrep. And remember, all these things we have said about irreps before goes. We are using Greek letters alpha, beta, etc. to label the irreps. And when we label an irrep, we are going to say that two irreps with different labels have to be inequivalent. If they're the same label, they're the same irrep. Now, with some abuse of language, I'm going to say, instead of the subspace which carries an irreducible representation, I will sometimes say the irrep itself, because frankly, a subspace is a set of vectors on which this irreducible representation will act. However, what we often do is deliberately confuse the two, simply because otherwise the language would become too cumbersome. And we could say, okay, I can have basis vectors like v alpha 1, v alpha 2, v alpha d alpha, where d alpha, of course, is the dimensionality of the irrep. And these will give me a basis of a subspace in which every vector transforms under the group element in group actions into a vector in this subspace. In fact, it transforms exactly according to the rule which this particular irreducible representation gives you. So what I could say is, if I knew all the irreps which build up my particular reducible representation, I could just take their basis vectors, so something like v alpha k, and put them all together. So k will run from 1 to d alpha, and then alpha will run over all possible values which alpha can take. And you know how many different irreps there are, right? Then have at most, in fact, you have exactly as many irreps as the number of classes. So alpha k will go from 1 to d alpha, as I have said, and alpha will go from 1 to all the way up to nc, when nc is the number of classes. And that will give you a basis of your V. This is a basis. Original vector space. But can you see something wrong with this? If you have followed what I am saying so far, you should be able to see that there is a gap in my reasoning somewhere. For example, if you looked at if you looked at the example that we talked about right now, how many basis vectors? You have three reps, right? A1, A2, and E. How many basis vectors does a space which carry A1 have?
One.
One, because A1 is a one-dimensional representation, right? It can have only one. A2, how many?
One.
And what about E, the third representation?
Two.
Two, of course. So you have 1, 1, and 2, right? But that gives you only 4. How many do you need? When you talk about reduction
6.
of this particular, you need 6, right? You need 6 basis vectors. You already have 6 basis vectors, E1, E2, E3, E4, E5, E6. What we want to do is go over to a new basis where the new basis vectors will transform nicely under all these group elements, so that it will be able to exhibit the block diagonal structure automatically. That means basically these basis vectors will have to actually be individual basis vectors for the invariant subspaces. Fine, but 1, 1, and 2 definitely don't make up 6, right? So you have VA1. I can put a 1 label here, but there's only one VA1. That's fine. There's one VA2. Now when I have VE, I have one VE2, right? So where will the other two come from?
You have 2 copies of E, right?
Exactly. You have 2 copies of E. That means in addition to VE1, VE2, there will be 2 more basis vectors. Let's call them V prime E1, V prime E2. And why are they both labeled E? They're both labeled E because when you do a particular, simply because when you do, let's say, LG, take some group element, apply LG on VE1, what you're going to get is basically some matrix element, let's say alpha 1, 1. But if you, and I will get a similar relation for VE2. But if I did the same thing, if I apply LG on V prime E1, if this is correct, can anybody tell me what LG actually on V prime E1 will be? Of course, the numbers alpha 1, 1, alpha 1, 2 you can easily figure out, but that's not really important right now. If this is the way VE1 transforms under the action of LG, how would V prime E1 transform? Remember what we are saying is this one and this one both give you both span invariant subspaces which carry the same representation, namely the representation we have labeled E.
So it should be some constant V1 prime V1 plus.
So V prime E1, some constant, let's say beta 1, 1,
and
like that.
Beta. Given that we know that it's an irrep and it should sort of
exactly. Okay, it's an invariant subspace, so it has to be that. But you are missing one point. We have already said that these two, this one corresponds to the irrep E. This one also corresponds to the same irrep E. So the same irrep must be somewhere here, right?
Sir, I don't understand your last point. What is it that you're saying?
No, first of all, the fact that these two belong to one irrep means whenever you apply LG for any G on VE1, you are only going to get VE1 and VE2, nothing else. Fine. So that's why you have two pieces here and two constants, right? And the
Yes,
same
sir.
thing goes for this. That much I
Yes, sir.
agree. But I'm saying it's not just, you're not just saying that these two belong to one invariant subspace and these two belong to another invariant subspace. That's true. But on top of that, there's an additional thing that you have said. You have said that these two make up an invariant subspace which carries an irrep E. And these two also carry an irrep E. Right? So the fact that it's not just these two form a two-dimensional invariant subspace and these two form another two-dimensional invariant subspace. What is critically important here is these two actually carry the same irrep.
Sir, I
So
think
that
we'll do
information
4
is
direct sums.
Hmm?
As
No,
in,
that's why your direct sum is fine. 1, 1, 2, 2. That's 6 spaces vectors. They give you a 6-dimensional space. But in terms of this transformation, this is very critically important. When you say these two belong to the same irrep, two copies of the same irrep. What does this two copies of the same irrep mean? By the way,
Alpha should be equal to beta.
alpha should be equal to beta. Close. Not very
Alpha
perfect.
complex conjugate.
No. The original
But
thing,
we aren't dealing with something which is complex numbers to begin with. Like, we're not dealing with a complex space.
we could, but right now we are not. But in general, we could. But complex conjugate is really not correct. What is closer to being correct was what was said first. That is, these numbers should be exactly the same. When you say they transform along according to the same irreducible representation, you mean they transform exactly the same way when you do a group operation. Just like, why do you think the two different things are vectors? Why is force also a vector and momentum a vector at the same time? Because they behave the same. Why do you call them vectors? Because they behave the same way under rotations. Similarly, why are you saying that these two and these two carry the same irrep? That simply is a statement that they transform the same way under the group operations.
Sir, do you mean to say that V1E and V prime E, V prime 1E are like equivalent vectors?
You may use that terminology, but that's not really very relevant here. All I'm saying is the way in which V1E transforms. V1E, of course, transforms into a combination of V1E and V2E, whereas V1 prime E will transform into a combination of V1 prime E and V2 prime E. Okay, that much only follows from the invariance of the two subspaces. But the fact that they carry the same irreducible representation in this particular example, of course, where we are using S3, we know S3 has only one two-dimensional irrep, but there are many other groups for which you may have two different two-dimensional irreps, right? If these belong to two different two-dimensional irreps, let's say E1 and E2, let's say, then you would not claim that these coefficients would have to be the same. The fact that they belong to the same irrep essentially means that they behave exactly in the same way when you when you apply your group actions. Is that clear?
Sir, I'm still slightly confused about how we even came to V1 prime and V2 prime.
Well, your original
Slightly.
space was 6-dimensional, right?
Yes, sir. That was 6-dimensional.
So that will break up into invariant subspaces.
Yes, sir.
And how many invariant subspaces does it break up to? That, of course, is something you calculated using the character table, but we knew that because regular representation already has that.
Yes, sir.
Two one-dimensional representations, A1 and A2, occurring once each, and the only two-dimensional irrep which this particular group has to occur twice. What does it mean when it occurs twice? It means that there are two invariant subspaces, two distinct invariant subspaces, both of which are two-dimensional, and both of which transform exactly in the same manner using the same transformations under the group action. Is that clear now?
I think I'll have to
Okay,
go
wait.
through.
Hopefully, when we go to the projection operators, we will see the surfaces anyway. So maybe that will make it even clearer.
Okay.
But there's one thing I did say. I said this is almost correct. The fact that the betas have to be exactly the same as alphas, that they have to be exactly the same as alphas. That's what I said. There is a small catch there. Can anybody spot how this statement can be made more precise? Any ideas? Or what is sort of imprecise about this statement? After all, we are saying they carry the same irrep means they transform the same way. Two vectors carry the same irrep of the rotation group. That is exactly why they transform the same way under rotations. Here we are just talking about some other set of group operations, not all rotations. But the same idea works. So why am I saying that there is something slightly loose about saying that LG V prime E1 has to be this if LG V E1 is this? Yes?
Sir,
Yeah.
sir, I have a bit of confusion. We have two copies of E, right?
Yeah.
And those two are representations in two-dimensional subspaces.
Yeah.
Okay, so when we
that means
take
there are
E1,
two different two-dimensional subspaces of this particular six-dimensional subspace, in both of which the vectors transform among each other only and in exactly the same way as what the irrep E would tell you.
okay. So if I were to think, I mean, V1 and V2 are the basis vectors. I mean, one type of basis vector, like let's say 1, 0, 0, 1, and V1 prime, V2 prime are two other basis vectors. I mean, two other perpendicular vectors.
Not necessarily perpendicular,
right.
but let's not. Two other basis vectors. Yes.
Two other basis vectors. Okay.
Yeah.
But then V1 and V1 prime and V2 and V2 prime cannot be linearly independent, right?
They have to be. They are two basic.
As in,
by the way, as I was saying, you are breaking up the original six-dimensional vector spaces into invariant subspaces, right? V1, VE1 and VE2 span one two-dimensional subspace. V prime E1 and V prime E2 span an entirely different two-dimensional subspace. Okay.
Okay. Yes.
So they are definitely independent vectors. But because they actually respond in the same way because they belong to the same irrep of the group G. And after all, there are only finite number of irreps which a particular group can have. So it doesn't have much of a choice. These two have to belong to the same irrep or have to transform under the group according to the rules of the same irrep. Okay, that doesn't make them dependent.
Sir, should we make them satisfy the homomorphism condition? If let's say I'm applying LG on like a product of V1 prime and V2.
That you have to. After all, these are group representations. They have to satisfy the homomorphism condition. But the homomorphism condition only becomes important when you have multiple group elements, right? LG1, LG2. Of course, this is for only one group element. LG may be alpha 1, 1, alpha 1, 2. For LG G prime, it will be alpha prime 1, 1, alpha prime 1, 2 here. And those matrices will have to obey the homomorphism theorem. Probably, and that is why you have such great look. Why do you have only a small number of possibilities? Because the homomorphism requirement puts in a huge amount of restriction on the possible matrices that you can have here. You can't just write down any matrix, any 2 by 2. After all, this will be a 2 by 2 matrix, right? When I've just written down two elements here, but for VE2, I'll get two similar terms. So I can write a 2 by 2 matrix for corresponding to LG. But I can't just write down any arbitrary 2 by 2 matrix and claim that is going to represent my group element. The homomorphism condition is definitely there. I'm saying, okay, after you obey those homomorphism conditions,
Sir,
if you have
can
these
I change
numbers,
my statement?
Yeah.
I'm sorry. So what if we apply LG on like a sum of V1 and V1 prime so that they sort of group in alpha 1, right?
Yeah,
I don't know.
that's actually the direct sum representation.
Oh, okay.
We have talked about that. There's nothing very new about this. That's exactly what this reducibility means. That you could start with you could start with smaller subspaces or smaller spaces on each of which you have a representation, and then combine those smaller spaces by using a direct sum to get a big space. That will give a representation on the big space. Or you could just look at it the other way around, say that, okay, I have a big space which can be thought of as being decomposed of invariant subspaces. Each of the invariant subspaces carries a representation. The big space carries a direct sum of those representations. And that is what reducibility is. Whether you can reduce a representation on a big space into a direct sum representation of others. Okay, so all these concepts tie up together. They are not independent of each other. No, the only thing, okay, let me just quickly give you the answer to what I was trying to say. The only real thing that really is an issue here is the particular form that the matrix elements take. These are, of course, matrix elements, right? Is everybody clear about that? That is, if I wrote down this and also wrote down the expression for VE2, what happens to VE2 when you apply LG? Then you'll get two more coefficients, and with these you'll get 2 by 2 matrix, a 2 by 2 matrix, right? Is that okay with everybody? Actually, I shouldn't have called it. I'll call this alpha 1 2 perhaps. Not perhaps. I shouldn't really have called this alpha 1 2, because as you all know, the basis vectors transform like this, right? That's how you define the matrix elements. Is that okay? But this will give a 2 by 2 matrix. This will also give you a 2 by 2 matrix. Now, the fact that the two irreps are identical, does it mean that they have to have identical matrices? Is this question clear? If two representations are identical. Yeah.
Are you saying the columns can be interchanged?
No, I'm not saying that. I'm saying that much more than that. If two representations, the point is these two basis vectors, they span a space which carries a particular representation of the group. That representation happens to be irreducible, but ultimately what we need right now is that they form a representation. Okay, and these two form another representation. Okay, they form an identical representation, but the identical representation, does it always lead to the same matrix? These numbers here are matrix elements, right? But do identical representations, or think of even one representation, does a given representation always have one set of matrices? Or is it possible to have multiple matrices which also talk about the same representation?
It is possible.
Equivalent.
Are you talking about similar transformations? As in,
Yeah.
like between V1
Equivalent
and
to
V1 prime? Are you
Equivalent
talking about?
Okay, basically, what all of you are saying are the same thing. Basically, the matrix that you get depends on your choice of basis, right? Now, so if you change your basis, the same transformation will look like a different matrix. Okay? Yeah.
Yes, sir.
So what we are really saying here is something rather simple. We are saying just hold on. Hello? What the hell? What I'm saying here is simply this. The precise numbers that you get here, LG V2E is alpha So this gives you the matrix alpha 1 1, alpha 2 1, alpha 1 2, alpha 2 2, right? You go down the column. That is why the labeling was done this way. And this gives you DG, a two-dimensional matrix. And because we are saying that V1 prime and V2 prime carry exactly the same representation, we were saying the numbers here must be the same. Except that here you will have V prime 1, V prime E, V prime 2, and so on. But other than that, the same numbers. But let's be clear. Do I have to have the same numbers? Exactly the same numbers. Is that essential?
Not necessarily.
Not necessarily, because you could just, because these are two different spaces, right? So you don't have to choose the same basis. You could
Yes,
choose a
sir.
different basis.
Yes, sir. So you mean to say that if I know how V1 transforms to V1 prime,
No,
then-
V1 does not transform to V1 prime.
No, sir. I mean just a similarity transformation between these two subspaces.
So
with
basically, the
two-dimensional.
point is, okay, what you're really saying is okay, except that you're using the wrong language. You can't transform V1 to V1 prime. But what you can always say, that in the other subspace, there's always a pair of basis vectors which will exactly transform the same way as V1E and V2E did. And if you change your basis there, you would end up with some numbers which may look different. Simply because there's an S and an S inverse sitting on here, which will make it the same as this.
Yes, sir. That's yes.
Okay. These are in different spaces, so you can't really transform V1 into V1 prime. But in the second space, there will be a pair of vectors which will form a basis, which will transform exactly the same way as V1E and V2E did. And basically, what will happen is that you may have chosen that basis already, or you may choose some other basis. If you choose some other basis, then the numbers will not look exactly the same. But you can always make them look exactly the same by choosing your basis properly. Okay. So what I meant was, it's not precisely correct to say that this has to be, but what is precisely correct is that you can always choose your V prime E1 and V prime E2 in such a way that this will happen. Okay. Does this make sense?
Yes, sir.
Okay. Now, that means, after all, you have 6 basis vectors. That's the point that we were trying to really make for so long. And these 2 basis vectors, no problem. For these pairs, you have to write primes, perhaps. But primes only work if you have only 2 copies. But maybe you have, in a more complicated representation, you may have 20 copies of a particular irrep occurring 20 times. That means, of course, means that your representation has to have a very large dimension, enough to accommodate that many basis vectors. But then using primes will not be a good idea, right? Because you will just simply run out of, or get bored writing that many primes. So what we usually do is something like this. Instead of writing V alpha, K, etc., we just add another superfix here. But this M essentially tells you which copy of the irrep you're talking about. Okay? Is that clear? So in this case, I will just use 6 basis vectors, and the 6 basis vectors will be, here the index 1 is redundant because you have only one copy, one element anyway. Same here. But then you will have VE1, 1. So these two span your first subspace, and VE2, 1, VE2, 2. These two span your earliest other subspace. These were what we were earlier calling V prime E1 and V prime E2. Okay, clear? Now, if you had only 2 copies, then even a prime would be good enough. But if you had many copies to worry about, this is a notation which sort of allows you to keep on using any number that you want. Okay?
Sir, I have a doubt. Like, why?
Go ahead.
We took the copy for the 2-dimensional representation, right?
Yeah.
Why can't we take a copy of the one-dimensional representation.
Of course you can, but not here.
Uh,
Because this particular representation from the character table itself, I can figure out how many copies of each element, each irrep occurs there. Are you asking, can I do this in principle for some other representation? Of course I can.
okay,
I'm talking about a specific representation here, right? As an example, I have a specific example in mind.
Okay.
That example we know has two copies of the two-dimensional representation, one copy each of each one of the one-dimensional irreps. That is why this has this choice of basis. In general, it's very possible that the one-dimensional irrep will occur 5 times. Or in one of the one-dimensional irrep occurs 5 times, another one-dimensional irrep occurs 20 times, and a two-dimensional irrep occurs 15 times, let's say. That's very possible. Okay, this particular basis choice is for the specific example we have talked about.
Yes, sir. Yes, sir.
Okay, but your point is that I guess your point is, do I really need a second index only when we are talking of two-dimensional irreps? Of course not. Here I did not need the second index suffix simply because they were only one copy. There could be multiple copies in general. So, which is why usually what we will do is we will write the basis vectors like this. Okay, this is the notation that could be very confusing if you just saw this for the first time. This looks rather a lot of indices and makes no sense as to what they mean. But this tells you which irrep is it that my basis vector transforms according to. This tells you which copy of that irrep are we talking about. So if there are multiple copies, you'll have multiple values which M takes. And K is which basis vector within this particular irrep. So basically now we know that K will go from 1, 2 up to d beta. M will go from 1, 2 up to m beta, where m beta is simply the number of copies of the beta irrep in my representation. And finally, the other index beta, all possible values nc. Actually, m can also be 0, right? Because a particular irrep may not occur in your representation. Is that okay? So what I'm going to say, this is okay. All this background was basically to establish one point. An arbitrary vector in your vector space can be written down as this in this rather intimidating looking form. Okay, can anybody tell me what the limits will be on this? What I'll be summing over, and what are the limits? Say I'm summing over K, for example. What will be the limits for K?
K would be from 1 to d beta, the dimension of
the beta representation, beta
yes.
irrep, right?
And then
Of the irrep beta, not the beta irrep, of the irrep beta. M will go from?
M will go from 1 to the number of copies of...
Actually 0 too, but if it doesn't occur there, I will just not use it, I guess. Okay.
And beta will go from 1 to the number of classes.
Well, actually, that's the maximum it can go to. Usually, not all irrep may occur in a particular representation. In my example, that we had that was effectively the regular representation, and the regular representation has every irrep in it. But
so it can go from 1 to n, where n is less than or equal to nc. So
yeah, but anyway, you can make it go up to nc and it just insists that if an irrep does not occur there, if a particular beta is not in this particular thing, you will just put in m beta equal to 0 for that. That's just a notational thing. But this rather cumbersome looking thing, if you look at it once you've broken it up, all you're saying is that you can choose your basis in such a way that each of the invariant subspaces have their individual bases, and we have put them together to form the basis of the whole space. And this is nothing but the expansion of a vector in its basis of the vector space, right? but for a very specific choice of basis, namely a set of basis vectors which span the invariant subspaces. Okay?
So technically, we're just trying to figure out a nice odd way to order these.
Not really. What we are really trying to find out is something which this notation a bit hides a bit. Point is, I may know my vector space. I may have a basis on that vector space. But this is a very specific basis I'm talking about, right? And ab initio, I don't really know these basis vectors. All I know that there has to be such basis vectors.
Oh, yes.
Okay. So really, our job would be to try to figure out what these basis vectors are. Okay. I want some kind of algorithmic procedure which will tell me, given a vector space, given a representation on that vector space, how do I find out these basis vectors which span the invariant subspaces? And that is all there is to this job. That is all I'm talking about, how to find these things out. Okay. The way I've written this down, it sort of looks like we already know them and we are expanding V out in terms of them, which is fine. We know that they will form a basis, and given the fact that they form a basis, I can always write any vector in terms of them. But our job is not to actually start here and get to a vector V. Our job essentially is to find out what these are. Is that clear? Okay. I hope that's clear. So to see how you can find this, that's the actual thing. Let's apply. First, let's apply LG on this, on the vector V. What will happen? You have this sum over beta m and k. I'm not writing the limits because they're going to be these anyway. LG acts on this. LG is a linear operator. So what does it do? It simply goes into the sum, ignores the coefficients, goes and hits this, the vectors. But now that you have this, can anybody tell me what this is going to be? Or how you can rewrite this quantity? First of all, when LG acts on Vk beta m, LG is acting on a vector in your space, so it has to be a vector in the whole space somewhere. But it cannot be a vector in the whole space somewhere, right?
It needs to be. It will split up according to the invariant subspaces.
So it will stay within. So this particular vector, if I forget the sum for the timing, if I focus on a particular element here, there's a particular vector in a given invariant subspace. When LG acts on that, it is going to give you a combination in that particular subspace, right? Okay.
Yes, sir.
So what, and we already know what that is going to be. That is actually going to be right? Note, different case, it was a fixed k, this is the sum over all possible j's, right? So this index has changed. But what has not changed is, of course, the irreplaceable beta stays the irreplaceable beta throughout. All these v's belong to the same irreplaceable. Not only that, it belongs to the same copy, same m. That's simply the statement that each of these span a given invariant subspace on its own. So same m, same beta. All the different vectors which make up that space, you can expand in terms of that. And what is important, of course, is this is exactly what we were saying about how E1, VE2 transform compared to how V prime E1, V prime E2 transform. We are going to assume that we have made life simpler for ourselves. We have chosen your basis vectors. We are finding the basis vectors here, so we can always choose to find specific combinations, we will choose to find them so that all of them transform according to same matrix. Same meaning, for a given beta, all of them transform in the same way. You change your irrep, then you get a different matrix. Otherwise, for a given matrix, it's always the same. Even given irrep is the same transformation. Is this clear? Is this piece making sense?
Yes, sir.
Okay. Now you have one djk beta g, right? So because you have a dgk, or maybe what I will do is I need the index j later. So I will just use the fact that this is a dummy to rewrite this as L equals 1 to d alpha dlk vl. Okay, fine. But now that you have this, what is our most important tool at hand for anything that we do with representations? What do we want to use here? If you are talking about representation and you want to figure out properties of the representation, there is really only one tool which we can use in various incarnations. And the tool, of course, is the great orthogonality theorem. For that, what we need are two Ds, right? Remember, that was what this was. D alpha I. So this summed over all group elements. That was mod G by D alpha delta alpha beta delta II prime. So I've got d beta LKG. Okay. Here, I need two D's, and then I need to sum over the group to get the great orthogonality theorem to help us out. Right. So what do I do here? If I want to somehow get the GOT to occur, to be used here, I must multiply both sides by d alpha. So let's just take this expression itself. Let's do one thing. Just change the pen color. Okay. I multiply both sides by d alpha ij g inverse. I can always do that, right? I can multiply by a number, nothing wrong with that. And then just get some space here. Okay. And simply sum up. Is that okay? I can always do this, right? I can always, when two things are equal, I can always multiply them by some numbers. These are, of course, numbers, by the way. It may look pretty intimidating with just so many indices and all that, but this is just a single number, one for each group element, and then I sum up over all group elements. Okay? Is everybody following this? And then all I do is change the order of summation. This summation was being done first, and you were doing this summation at the end. But what I'm going to do is just do the group summation first. I'll do after that. And when I do the group summation, inside the sum, I will need to keep only those things which depend on the group element, which is this one and this one. Everything else are independent of everything else here, the CKs and the VLs, they're independent of the group element, right? But what is this? This, of course, is okay, delta IL. In this version, the original version of the great orthogonality theorem is the two extreme indices, L here goes with J here, sorry. L go the first index with the of the one with the G goes with the last index of the one with the G inverse, and the other two go together. So this is what is sitting here. And you have to do a sum over beta, M, K, and L. The sum over G has already been done, that has yielded this. So now tell me, now each of these is, okay, so I have 4 things to add up over beta, M, K, and L. And 3 of them have delta symbols in this expression, right? So at least 3 of the sums will be trivial. The sum over beta, the sum over K, the sum over L. The sum over M will still survive. You will still have a sum over M. So what will the sum be? It will be mod G by D alpha. What the delta alpha beta will do is, when you're summing up over beta, is that all the betas will become alpha. So you get C alpha here. M you're not summing up over anyway. And V alpha M. And what happens to the indices? This L becomes what?
J.
And what happens to this K?
I.
Okay, so that's it really. So what we have is an operator. Let me just define that operator. P alpha. This operator, of course, depends on which particular representation you're talking about, which particular irrep, and which indices. So P alpha ij, which is by definition sum over the entire group Remember, when you had an original representation, you had operators for each group element. So what you're really doing here is you're multiplying each of those operators by some weighting factors. Okay, D alpha, ij, G inverse, which are just numbers, right? And summing up over all the group elements. So this is some kind of weighted sum of these operators LG. And when you take all of them together, you get this projection operator. Why am I calling this a projection operator? So what does it do? Let's see. Acting on the vector V, which is of course what you calculated here. This is the P alpha ij. This is acting on the vector V. What you're going to get is mod G by D alpha Now, can anybody tell me why am I calling this a projection operator? Just remember that V originally so this is the vector V on which you are applying this P alpha ij. And when you do that, what is really happening? It's even easier to understand if you just imagine for the time being that this particular irrep I'm talking about may have only one copy. Let's say M only occurs once. M alpha is 1. So there's no sum. Then what is this vector? Then P alpha ijv is?
Technically the weight, it technically gives the CIs in some sense.
We are not really interested so much in the CIs. CIs are just numbers. But we are much more interested in this. Apart from an overall number, CI is a number, mod G by D alpha is also a number, right? Fine, it's some number. But what is important is it's just some number into a vector. And what is that vector? That vector is a jth basis vector of the alpha rep. So the point is, you start with an arbitrary vector V and apply this P alpha ij on it. the resulting vector is going to be one of these basis vectors we are looking for. You will have some number multiplied in front, but I don't care about that anyway. The length can be adjusted. And after all, if you have a bunch of basis vectors, you can multiply them by any constants. They will stay basis vector as long as you're not multiplying them by 0. Yeah. Is that right? So of course, the tricky thing could be that these constants Ci you may have chosen your original vector V in such a way the C alpha Mi was 0. Well, then this will vanish. But if your original vector had some non-zero value for C alpha Mi, then you are going to get a vector which is exactly in the same direction as V alpha Mj. In fact, I can use that vector as V alpha Mj. Does it make sense? Yes? Okay, let me just try to give you a quick example of this, since I've already taken up more time on this issue than I should have, perhaps. Let me just give you an example of this in action, and it should be pretty clear what we are talking about. It's pretty easy, actually. This is making it sound a lot more complicated. But before I go there, just one point. If your irrep is an unitary irrep, then of course d alpha ij g inverse is the same as d alpha ji g's conjugate. So you don't have to worry about g inverse. G itself will give you what the thing is. Number one. And number two, how many projection operators do I have for a given irrep? For the irrep alpha, how many do I have?
D alpha.
No, how many do I have actually? How many values can I take?
D alpha times D alpha.
Yeah, we have D alpha square projection operators, right? And of course, how many basis vectors do I have in the alpha theorem, where this is going to land me in?
M alpha.
Not M alpha. M alpha.
D
times
alpha.
D alpha. It's actually M alpha times D alpha, right?
Oh, yes.
Because you have M alpha copies of those. So the point is, you don't really need all these D alpha square projection operators all the time. Very often, you just stuck to P alpha II. Not just very often, always. P alpha II is enough. That is, instead of using I and j differently, just use different values, or just use this. Just use the diagonal elements for the inverse, or if you are using unitary representation, just the conjugate LG, and that's it. And that will do the job for you fine. So, okay, enough talk. Let me just illustrate what I mean by all this. Let's say, let's go to our equilateral triangle, and let's start with an arbitrary vector. Let's say this vector, a horizontal vector like this. And let us try to apply our PA1. Of course, for PA1s, writing 1, 1 is redundant because A1 is one-dimensional, so there are no multiple choices. But just to be consistent, I'm writing this as PA1, 1, 1. Okay? Which is what? Which, according to this formula, is going to sum over every group element, the LGs, after weighting them by these coefficients. Okay, what are the coefficients in this case? If A1 is our first irrep. So what are the coefficients? Quickly. These are matrix elements that you require, right? What are the matrix elements for the irreps? They're all 1. That's a trivial representation, right? The representation in which every vector stays the same. So this one is simple. This is LE plus LA plus LB plus LC plus LD plus LF. 6 operators added together, just added together. You should weight them by the coefficient sitting here, but the coefficients are all 1. So this is your projection operator. Done. So let's see what this projection operator will do to this red vector. So what happens to it when you apply LE?
Stays the same.
Stays the same. You don't even need any mathematics for this, just pictures enough. Okay, this is the vector A. This is a reflection about A is this one. So when LA acts on this red vector, it gives you this vector, right? So this is LE acting on A, this is LE acting on B, this is LA acting on B. Yeah? Okay, this was what we called B, right? Reflection here. So what will it do to this red vector? I hope you can still see the red vector peeking in. So it will move to this corner, right? First, when you're reflecting along this point will come here and it will point this way. Is that okay with everybody? Does it make sense?
Yes, sir. Yes.
What about LC? LC is this reflection. This point will go here, and now okay. Now 120-degree rotation. LD. So this point comes here. And when you rotate this red vector through 120 degrees, which way does it point? Think of rotating this to 90 degrees, which way will point? It will point right up. 120 means it will turn through 30 degrees more. Of course, not here. It will come here. But which way will it point? This is 90 degrees, right? Vertically up. You had a horizontal vector. Once you rotate it to 90 degrees, it will come here. It will point in this direction. Through 120 degrees, which way will it point? In comparison to this one?
It will be parallel to the lower.
Yeah, it will be parallel to this side, but it will be exactly opposite LCV. So LFV, the only one left. Can anybody give me that? First of all, this point will move all the way to 240 degrees, all the way to this point. And this vector will turn to 240 degrees. This is 180, 60 degrees more. So which way will it point? Yes?
Opposite to LBB.
Exactly, it will point this way. So not LD, this is LF. Yes. So if you want to find out what the projection operator does to this vector V, you have to add up all these 6 vectors. And what do you get when you add up all these 6 vectors? The 6 arrows I have drawn?
0.
0. Okay. Not very successful, because if we had found a non-zero vector after this, that would be a vector which would span my one-dimensional, one of the one-dimensional invariant subspaces, the one which carries the representation A1, identity representation. All this is telling me is that I started with a vector that was this horizontal one, which had exactly 0 coefficient in the direction that we are looking at. The one which we are looking for, we don't know that as yet. But what we do know is that this red vector had absolutely no component in that direction, which is why when I applied PA1 on that, I end up with 0. Okay? Yeah? This one was not successful, but even failures teach us things. That's what I'm trying to say. Okay? So is there any question about this? Because now we will use. Okay, this didn't work, right? So how would we actually make this scheme work? I do want a vector which I get as a result of applying this. How do I get that vector? Remember, I have to apply this thing on some vector to get a resulting vector which would give one of the basis vectors, in fact the only basis vector, this being one dimensional, which carries the identity representation or the representation A1. So how would I get this to work? This one didn't, right? You applied PA1 on V and you ended up 0. With 0, that of course that is fine. You can get 0, but 0 is not what we want, right? That will not be a basis vector. Then what else can we use? What else can we do? Any suggestions? Let me just remind you, this was our basic aim. PA111 acting on V, whatever vector this gives me, that vector should actually carry my one-dimensional array A1. And I started with a V, this one, and fell flat on my face because I ended up with 0.
So should we find a vector that will give us a non-zero projection in some sense?
Exactly. Or just the usual thing to do is just try some other vector. Okay,
So,
in fact, the chances that you're going to get 0 is actually very, very tiny. Okay. If you just started with a random vector, you would not have got 0. You've got a 0 because you started with a very specific vector, the horizontal one. Okay, the horizontal one didn't work. Let's try the vertical one. Okay. Let's say this is your V. So this is your LEV. This is not only V, this is also your LEV, right? What about LAV? What is that? Reflection along this line.
The same.
Same. Okay, good. At least now LEV and LAV are not cancelling each other out. At least this gives us a glimmer of hope. LBV, reflection in this line. First of all, okay, let me just label the corners it will make. If this is alpha, this is label with corner A, corner B, corner C. Which corner will it go to?
C.
It will go to C, right? And which way will it point? Can you describe that? The reflected vector? In terms of the three lines that are drawn, three dashed lines that are drawn on this triangle, can you tell me which way will it point?
Along the median C.
Yeah, but not along the median, in the opposite direction, right? This is your vector. When you reflect, it will point this way. Not this way, right? This one was away from the triangle. This one will also be away from the triangle. Is that okay? Okay, but you can see that there is one more symmetry operation which is going to give you exactly the same vector. Can you tell me which one?
The 240-degree.
Yeah, the one which we called F. Okay, what about C? It will give you, okay, that's sort of trivial, along this median. And LDV will also be that. So when you add all of them together, size doesn't really matter, but when you add all of them together, you get a vector which is the sum of these three vectors. Right? You take this vector, not this vector alone or this vector alone or this vector alone, but the sum of these three vectors is invariant under the action of all of LE, LA, LB, LC, LD, LF. Got it? So the specific vector, of course, you can write it down in terms of the original E1, E2, E3, E4, E5, E6. Say 0 E1 plus 1 E2 plus some combination of E3 and E4, some other combination of E5, E6. Not really very important. What is important is the geometrical fact that the basis vector of our six-dimensional space, of one of the basis vectors of our six-dimensional space, which spans an invariant subspace, in the ident and carries the identity representation, is this particular basis vector. And when we talk about the physical applications in molecular vibrations very soon, this will give you a particular mode of normal mode of vibration. What is that? We have actually talked about this before. I don't know whether you remember this, but this particular mode of vibration essentially captures a particular way in which the molecule changes. What happens to this molecule if this were the displacement? Suppose this red one was the original molecule. What happens to it after the displacement? It becomes this bigger triangle, right? Oops, bad drawing. And so what kind of motion does this give you? And of course, remember when it's vibrating, this is just a displacement at a particular instant of time. This displacement will change. But change staying within this subspace. So basically, and also it will go in the opposite direction. So it will also be something like this after a while. So what kind of vibration are we talking about here? Describe the shape of the molecule when this vibration occurs. The red one was the original size, original shape. After a while, it became something like this. And then after more time, it became something like this one. So what is the kind of motion that we are talking about? This particular mode of vibration has a special name. But if you can imagine what this motion is, you should be able to figure out what this vibration is. Come on, very simple. Okay, I will give you the name for this.
So, is it like a normal mode because it's...
It is a normal mode. It is not like a normal mode. These are precisely the normal modes. But I'm going to... But this is a complicated system, right? A triangular molecule with 6 degrees of freedom. The point is, this group theoretical thing can tell you exactly what kind of normal modes this can have. This is one of the normal modes. But what does it look like when the oscillation occurs? Imagine a triangle. What will it look like during these vibrations?
It will still look like a triangle.
Oh, of course, it will still look like a triangle, but then there are 3 points anyway, right? 3 atoms. But you mean it will still look like an equilateral triangle, right?
Oh yeah, it preserves the shape.
It preserves the shape, only the scale changes. This is called a breathing mode. Simply because just like a lungs expands and collapses as you breathe, here the molecule will sort of expand outwards, then come in, and expand outwards, then come in. A standard breathing mode of normal vibration. There is one normal vibration. Now the other ones, I'm not going to spend time discussing all of the other ones, but For example, I will just show you one of them, PA11. So it's a PA1. Let's look at PA2. What is PA2 going to be? Okay, I can put in a 1-1 index here, but doesn't matter. For that, you need the matrix elements once again for A2. But what are the matrix elements for A2? Anybody remember them? The other one-dimensional representation.
1 minus 1 minus 1.
Yeah.
Minus.
So +1 for all the rotations, -1 for the reflections. So what you had were so let's start with this is your V. This is also LEV, so that vector will have to be there. What about minus LAV? Which way does it point?
Same as LEV.
Yeah, it's exactly the same. So once again, good. This one doesn't seem to be cancelling. What about LDV? That's easy. LD is the 120 rotation, right? So it's going to point like this. Turn through 100 degrees, so we'll point in this direction. This is your LDV. What is LCV? LCV we had actually seen before. Plus LCV is just this. That's what we had last time. But what we want here is minus LCV. This is minus LCV, right? And this is what you're going to get from the other two. Okay, not for you. Let's see. LF. Okay, did I do it right? I didn't do it right. Nobody even pointed that out. Sorry. Completely messed that up. Not field, right? No, I didn't. This was 5. And 120, 240 degrees. LDV and minus LBV are going to be exactly the same. Remember, LDV and LBV were cancelling when you started with a horizontal V, right? That's why you ended up with 0. But here, because they are minus LBV, they add up. So when you add up, ultimately the normal mode that we are talking about is basically a vector in this direction, vector in this direction, vector in this direction. This kind of displacement. So, can you identify what kind of displacement we are talking about? This atom moving to the right, this atom moving this way, this atom moving this way.
Sort of a rotation.
It is a rotation. It's not sort of a rotation. That's one of the normal modes of motion. The triangle can rotate as a whole. Okay. This one we already knew. We didn't have to really do any group theory for that, but it's good to see that group theory is actually giving you back that. Okay, homework, because I don't really want to take up all your time now. With E, you will have PE11 and PE22, the two diagonal projections. For this, you will need the matrices E, right? The two-dimensional representation matrices, which we worked out a long time ago. Of course, you don't need the full matrices, but you do need the diagonal elements. So just the character will not do. When you're talking about projection operators, when you're trying to find out basis vectors for these irreducible representations, character table is not adequate. You have to actually fall back on the full representation. Because the character only gives you the sum of the two diagonal elements, right? So using this and this on some vector, usually take the horizontal vector through this vertex or vertical vector through this vertex, that's good enough. You should be able to figure out exactly what the other normal modes are going to be.
So, but then when we go into the E representation, the two-dimensional representation, then the weights sort of play an important role, right?
Of course. That is why you need to know the weight. That's why the weights play an important role in all of these. It's just that the weights were very simple in A1 and A2.
Yes, sir. So I mean, it won't be very easy to draw pictures.
Not really.
And, like,
It will not be very difficult at all. Because the weights
Okay.
are also pretty simple. The 2D rep, remember, is something you can generate just by using these two basis vectors and ask what happens to them when you reflect. So A1, for example, will just flip E1, keep E2 the same. So DA, the matrix, is simply -1, 0, 0, 1. Okay, not very difficult. So you, by the way, you don't need all the 4 elements. You just need the diagonal elements, -1 and 1.
So
Now,
I was talking about the A B, no, the
yes, say DB,
DNS.
for example, a 30-degree rotation. Sorry, reflection around the line which makes an angle 30 degrees. Half √3/2 minus √3/2 minus half. Sorry, plus √3/2 minus half. No, right. Yeah. So, by the way, complicated factors, right? √3/2s. But for the diagonal representations, you only need this half and minus half. Not very difficult. That's all you will need, by the way. Either ones or minus ones or halves or minus halves. You can always have a vector, right?
Yes, sir. So, but again, to sum up all of what you just said right now, what is this projection operator? I mean, projection vectors.
So the basic thing is you have some vector space which carries a reducible representation of your group. Now, this reducibility of the representation is important for many applications. In molecular vibrations, it's important because each of these invariant subspaces, they actually correspond to different normal modes. The theory of that we are going to do next. Okay, the precise theory which tells you this. What we are doing is we are actually taking the maths and trying to give you some physics glimpses so that it doesn't become all maths. But the maths is independent of whatever physics you want to use it for. But why is this important for us? It's important because for many physical applications, you need to know exactly which one of these vectors transform like this particular thing. Okay? It's not enough to just know. Okay, let's start again and say this. If I know that D is A1, direction A2, direction 2E, I know that in this 6-dimensional space, there is a particular vector which transforms according to A1, that is, which does not change at all under the action of LA, LB, LC, etc. Then there's another vector which transforms according to A2, which means that if you were to reflect that LA, LB, LC acting on that, you're going to get a minus sign. So these reverses under reflection stays the same under rotations. Then there are two vectors which form an invariant subspace which transform according to each other just the way these two vectors do when you rotate, when you carry out A, B, C, D, F on them. And then there's another set which does that. So there are two pairs of vectors which behave essentially like this pair E1, E2. Okay, that information is fine, but then the question is which ones are exactly those vectors? This information only tells you that there is a vector which will be such that it will not change under E, A, B, C, D, F. The fact that there is an A2 in the representation tells you that there will be a vector which will not change when you rotate, but it will change when you reflect. This one tells you that there will be a pair of vectors which will combine among themselves exactly the same way E1, E2 does under E, A, B, C, D, F. Just like all vectors transform in exactly the same way under rotations. Here, what we are saying are specific vectors which carry the representation E. You will have two of them which transform exactly the same way as E1, E2 does. And then there will be two more vectors like that. But How do we find them out? The answer is you apply the projection operators corresponding to each of these representations on some arbitrary vector. You may end up with 0. If so, hard luck. But if you don't get a 0, you get a vector which is which carries the representation A1. If you apply on an arbitrary vector, if you get 0, hard luck. If you don't get 0, then what you have got is one vector which transforms according to you have either got VE1 1 here or VE2 1 here. Now all you have to do is start with a different vector and get another. So if you start with two different vectors V here and apply PE11 and you end up with the same vector or a multiple, then again unlucky because you have essentially end up with the same result twice. But if you get two independent vectors, then you are done. Then you know that one of them will be VE1's one vector, the other will be VE2's one vector. And similarly, you apply PE22 on arbitrary V and keep going from there. So this is how these projection operators gives you the basis vectors for the invariant subspaces. I would suggest that you actually carry out this calculation yourselves. When I say actually carry out, I mean just take a large piece of paper, draw on it. Doesn't matter how bad your drawing is. These are pretty easy to sort of keep track of. Just draw. You don't have to do any calculations. Maths is fine. Algebra is fine, but you don't need algebra here. Just drawing is fine. Drawing actually tells you more about what you're really doing than doing a lot of complicated calculations using square root of 3s and stuff like that. Okay? So the homework is find out the other basis vectors as well. The fruit at the end of the work is A, you have reduced a particular representation completely, and B, in molecular vibrations, you would know exactly what the normal modes of the vibration for the symmetric triangular molecule would look like. Okay, any further questions? If not, let me just call it a day today. I see that the audience has already halved, which is expected. Did go too long.